Hello everyone and welcome to the channel. In this video, we'll discuss the bus enable pin of the CPU and how it impacts the logic of our databus demultiplexing circuit. I hope you enjoy! So in the last video, we finished implementing the bank address latching circuit from the datasheet, specifically the databus buffer, and we implemented it on a breadboard. So the logic of this circuit is functional, but it doesn't support some of the advanced modes you can use the CPU with. And I mentioned that I have some ideas about how to improve it. And the first one is to support the bus enable pin. So what is the bus enable pin? If you look at the datasheet of our processor, you can see that the bus enable pin is an input signal and it allows external control of the address and data buffers as well as the read-write signal. So when the bus enable is high, the read-write signal and the address buffers are active, and when bus enable is low, these buffers are disabled. So what does that mean? So the way you would use a bus enable pin in a 65C8610 system is if you want to implement direct memory access, DMA. So let's say you have, for example, a CPU and a GPU and a shared memory, which is the frame buffer where you store the pixel values of what you want to display on the screen. Both the CPU and the GPU need to access the memory in order to manage the pixels that you see on the display. And so this can lead to bus contention. The way you would solve that in the system would be to only enable one access at a time. And so in order to allow the GPU to access the memory to refresh the screen, you need to prevent the CPU from accessing the bus. And so you do that by taking bus enable low. This disables the address and data buffers in the CPU, and so the bus is free to be driven by the GPU. So the bank address latching circuit from the datasheet doesn't actually support this use case. Indeed, you can see that the latch is always enabled because we have tied its output enable to ground, and we see that the buffer is always enabled in the second part of the clock cycle. But when you bring bus enable low, both of those chips should be disabled so that the data bus and the bank address are free to be driven by an external device for direct memory access. So let's take a look at the changes that we have to make in order to implement this functionality. So this is the truth table of the circuit from the datasheet. We can see that we ignore the bus enable pin, and we see that the output enable of the buffer is active when the clock is high. The latch is latching also when the clock is high, and the latch is always outputting its contents. So those are the equations of our three output pins. Let's take a look at what it would take to take into account bus enable. So I've duplicated the first two lines, so the outputs are currently the same. And so now let's think about what we have to change in order to support the different state of bus enable. So when bus enable is high, we can keep the same content because that's what we were doing before. So nothing has to change in those two lines here. But when bus enable is low, we want the buffer and the latch to stop outputting their contents. And so we have to disable output enable on the buffer and also on the latch. So there you have it. This is the changes that you need to make to the truth table. Those are the corresponding formulas. You can see that the output enable of the buffer is the NAND of clock and buffer enable. The output enable of the latch is the invert of bus enable, and the latch enable hasn't changed. I will talk more about the behavior of the latch towards the end of this video. So how do we update the circuit to make this work? You can see here on the left the circuit we have currently implemented. And this is the new circuit. As you can see, it uses two inverter gates and an AND gate to implement those logic formulas. We can even implement it better because an AND gate can be turned into an inverter. And so this is what the circuit looks like using only NAND gates. So conveniently, we can use the 74IC00, which is a quad NAND gate, to implement the circuit and still use only a single chip, just the same as we did with the first version. So let's update our KiCad project. I have here the KiCad schematic where we left off in the previous video. Let's replace the single inverter we use with the new NAND-based circuit. Okay, so this is our schematic updated. Let's see how it looks like in the timing diagram. So this is a timing diagram where we left off in the previous video. It has the data of both the buffer and the latch. Let me remove the data that we don't need for this episode. If we take a look at the datasheet for the 74AC00, we can see in the switching characteristics at 5 volts that the propagation delay from input to output is at worst 1 to 8.5 nanoseconds. So let's update the timing diagram to reflect that. So this is the diagram using the 74AC04 inverter, which is a circuit that we currently built. And this is the diagram with the 74AC00 with the new circuit. So for the timing diagrams, I'm assuming that bus enable remains constant and set to high. I'm trying to study the timing of the CPU in normal operations. When we bring bus enable low, then the timing of all those components doesn't matter anymore because another system is accessing the bus, and so it's the timing of that system that matters. In our timing diagrams, we can say that bus enable is always high. So this is it. So if you notice, there's an issue here where we are not meeting the hold time of the latch. The bank address is available for 10 nanoseconds after the rising edge of a clock. And in order for the latch to function, it needs to be held at least 2 nanoseconds after the latch enable pin goes low. However, this can happen after 8.5 nanoseconds here, which if you add 2 nanoseconds means 10.5. So we're not meeting the hold time requirement anymore. However, we can be smarter than this and take a look at the datasheet again. We can see that the worst case of the propagation delay is indeed 1 to 8.5, but there's actually 2 rows here, and in the previous video I've never actually talked about what that means. The 2 rows are T propagation low to high and T propagation high to low, and there's actually a diagram on the next page that explains what it means. TPLH is when you have an output that goes from low to high, and TPHL is when you have an output that goes from high to low. The timings are actually different whether the output is going high or going low, and we can use that to our advantage here. If we look back at the timing diagram, we see that the case we're interested in is the latch enable pin going from high to low through the NAND gates, and so that corresponds to TPHL. TPHL, we can see, is actually much faster. The propagation delay is 1 to 7, and it's actually TPLH, which is the propagation of the latch enable pin going high, which is slower. So we can use that to our advantage here and resolve the hold time problem. And this is not actually something we can use for the other pins. For example, the direction of our buffer, because we don't actually know the direction that those pins are changing. It could be going from high to low, or from low to high, depending on whether it's a read or write cycle. And so we cannot make use of this distinction. So we have to use the worst case of both of them. So let me update the diagram. This is the diagram using the worst case of both scenarios, and this is the diagram using specific high to low and low to high propagation delays. So we can see that we're now meeting the hold time requirement on the latch, and the change didn't impact the output enable signal of the buffer that much. We already talked in the previous video about the timing issue that we have with the buffer. So we're gonna have to take a look at this signal in more detail anyway in a future video. So there is one more timing we can look at, and that is the behavior of bus enable taken independently from the clock. In the CPU timing table, you can find on the last line TBVD, which is bus enable to valid data, is a maximum of 25 nanoseconds. And so this means that the CPU, when you turn on bus enable, will take at most 25 nanoseconds for its buffer to turn on and for it to output valid data. And you can see there's a footnote here that says that bus enable to high impedance states, so that's the buffer turning off, is not actually testable, but should be the same amount as bus enable to valid data. So when the buffer are turning off, we can also assume that it's going to take a maximum of 25 nanoseconds for it to be valid. It would be interesting to see if our circuit is within those 25 nanoseconds or not. So I've started a new timing diagram here, which is specifically to look at the behavior of bus enable turning off and bus enable turning on, assuming a constant clock. And if we add the data from the CPU, we can see that in both cases, it will take a maximum of 25 nanoseconds, and the minimum is not defined, so it could be 0. So this is the behavior of a CPU, and it would be nice if our circuit would work within those 25 nanoseconds. So if we look at the latch, we know that the output enable is going through the same NAND gate as all the other signals, and so the timings are the same as we already have seen. And so if we look at the datasheet for the 74AC573 in the switching characteristics at 5 volts, you can see that the buffer turning on takes at worst 2 to 10 nanoseconds, and the buffer turning off takes at worst 2 to 12 nanoseconds. So this is the behavior of the latch. You can see that it will take at most 20.5 nanoseconds to turn off, and at most 17 nanoseconds to turn on. So we are faster than the CPU, so that's good. Let's take a look at the buffer. Again, we have the same signal going through the NAND gates. And we already discussed the timings of it turning on and off in the previous diagram. So this is the data. And so similarly, you can see that it will take 18.5 nanoseconds to turn off, and it will take 16.5 nanoseconds to turn on. So we're also faster than the CPU. So that's good. We're not adding any more delay than the CPU already has. Okay, so now we have everything specified. Let's build it on a breadboard. I'm going to remove the inverter and all the inputs that we forced high. And I'm going to replace it with 74HCT00, which is a quad non-chip. So we need to bring this line over one pin. Luckily, it still kind of fits. And we're going to jump over the clock here. So this is the clock coming in. We put it into the 2 inputs of the NAND gate, and so that's the inverted clock. So it can go to the latch enable just before. Then we need to add bus enable in the mix. So I'm going to take the clock again. Okay, I'm actually going to change this a little bit. So I moved the latch enable line to the bottom with the jumper for the clock. And then I just need to bring the clock over. There you go, so that's our inverted clock again. To rearrange those wires a bit. There you go. Now we need to bring the bus enable line over. And that's going to be pin 36, right next to the clock. Okay, so the clock NANDed with bus enable is going to be our output enable for the buffer. And then we want to invert bus enable to be the output enable of the latch. So this needs to come back here. Starting to get a bit tight. Okay, so this should be an improved circuit. We've fixed the control logic so that if we decide to use the bus enable pin, it will work out of the box. So now that we have the behavior of the output buffers specified, remember I mentioned I would talk about the behavior of the latch again. So if you think about it, the bus enable pin is taking the outputs of the CPU to high impedance. So basically they become floating. So if you look at our latch, the question becomes then, what is it actually latching here? Because the inputs are floating. And more generally, what happens with the CPU when you take bus enable low? Because if you look at the data sheet, there's not actually any mention of what the CPU does when you bring bus enable low. Does it keep running? How does it work? If you look at the internal architecture block diagram, you can see down there the bus enable signal is coming in and it's only affecting the output buffers. And indeed, the CPU continues running. But that's a problem, right? Because if it continues running, but it cannot access memory to read code or write data, then it's not going to work. And indeed, the behavior of the CPU when you bring bus enable low is not defined. It will just crash. So in order to implement DMA and use the bus enable pin, we have to stop the CPU from executing. And this will also help us resolve the situation with our latch, because if the CPU is stopped, then it doesn't actually matter what the latch is latching at that moment. There are two ways of stopping the CPU. The first one is just to use the reset pin, and that can certainly work. You can reset the CPU, disable the buffer, do what you want with the bus, and then re-enable the buffers and release the CPU from the reset state, and so it starts running again. The other pin that you can use for that is the ready pin. And that's going to be the subject of our next video. So I hope you enjoyed this one. Let me know in the comments if you have any questions or feedback. And I hope to see you in the next one. Bye.